Welcome students. Today we're discussing motion in 3-space, and 3-space is just an extension of our one-dimensional and two-dimensional spaces that we have been looking at. So when we talk about position, velocity, and acceleration, those quantities are just extensions of what we've been doing. Notice that velocity is just going to be, the velocity vector is just the derivative of our position vector, and then acceleration is the derivative of our velocity vector, which is the same as the second derivative of our position vector. Speed is just the magnitude of our velocity, and note that the magnitude of our velocity is defined as we have been doing it just in the past. In example 1, they want us to look at the two-dimensional motion given by this position vector right here. If you'll notice, that happens to be a circle of radius 3. So let's look at their beautiful little animation that they have for us in the text. Here's our circle of radius 3, so when they asked us to graph it, we can see our position vector, our velocity vector, and our acceleration. So let's take these off here so that you can see there's our position vector in blue, our velocity vector in red, and acceleration vector there in yellow. So let's watch it play. So at time 0, we are sitting here at time pi over 2. Notice we go around the circle, and 3 pi over 2, notice how the acceleration vector is always pointed towards the center, and the velocity vector is that tangent vector. So if I go back to beginning, I can watch it play, and we can watch those vectors, and the position vector is always pointed in the direction outward. Okay, let's see if we're up for finding the velocity and speed of the object. B, the velocity vector is just the derivative of our position vector, which we were given. So that would be a derivative of 3 cosine t for the x direction. That would be negative 3 sine t. Derivative of 3 sine t is 3 cosine t, and that would be our velocity vector. Now our speed vector, we're going to find the magnitude of our velocity vector, and that would be this quantity 3, whoops, I'll write that down. Alright, notice how this is just going to be, since this is our identity for 1, the velocity, the magnitude of the velocity or the speed is going to be 3. And we're given no units, so I don't know anything about that. So there's our speed. Acceleration is our acceleration vector is the derivative of our velocity vector. So that would be, I'm taking the derivative of this right up here, so that would be negative 3 cosine t, and then the derivative of our 3 cosine t would be negative 3 sine t. So we noted in our animation that the acceleration was always pointed towards the center or in that negative direction, and velocity changes as we go around the circle depending on what the value of t is. So we've already looked at this sketch in the animation. For our next problem, we're going to look at the animation from the textbook. I do want you to notice that little r of t, little r vector, is basically, you know, where I have t, I have a t squared in big R, and where I have a t cubed, I have a t to the 6 in big R. So notice that really it is capital R of t is little r of t but squared. So let's look at what that animation looks like when we graph these. Here's our textbook animation. We are going to watch this, if I can find my mouse, there we go. So we're going to watch this play out. We're going to watch how little r of t and big R of t follow the same path. They go through the same points, but at different times, because R of t, capital R of t is much faster. So at the beginning they're pretty similar, and then they're following the same path, but capital R of t gets to that place much faster than little r of t. So let me try it one more time. We'll show the grids and we'll watch how they both follow the same path. They both are following, they have the same points in common, but capital R of t is much faster. So let's find our velocity vectors associated with each. So the velocity vector associated with little r is just that derivative. So I have 1, 2t, and then 3t squared over 4. And then capital R of t is going to be 2t, 4t cubed, and then 6t to the 5th over, and I brought down the 6, and then I'm going to have, well, it's over 4. I could just go ahead and say 3/2, so I'll go ahead and write that. And then I'm going to look at the animation from your textbook. Now I could calculate the speed at various times by plugging in for t. I'm going to watch this animation. They don't ask us to find that, but you can find it in that way. So let's look at the animation. We can see how fast capital R moves in comparison to little r vector. Sorry, I cut myself off. Okay, let's show the velocity. I'd like to see it as we go along through here. Notice the little one, the green one is your little r and the blue one is your capital R. Notice how he finished long before the little r did. So we'll watch that one more time. Show velocity. So the green is little r and the blue is big R. Watch as capital R really takes off there at the end, and I'm still moving along for my little r. Still chugging on. And that is looking at the velocity vectors for each of those functions. Theorem 12.8 and its following proof are showing us that the position vector and the velocity vector are orthogonal at all times. And the proof goes through showing you that the position vector and the velocity vector will be equal to 0 for all time t, showing that they're orthogonal. In example 3, and that's what this picture is about, they're wanting you to show that the object moves on a sphere. So let's get the magnitude of that position vector. You can see that the magnitude of r is 5 all along 0 to 2 pi, so this means that we have a sphere of radius 5. Next we'll find the velocity and speed of the object. To find the velocity vector, I will just take the derivative of my position vector. So that'll just be, I'll write that down. Okay, I just went ahead and followed through with, here's my velocity vector, and I found the magnitude of my velocity vector, and the speed of the object is always 5 as it goes around that sphere. and you will note that the position vector and the velocity vector are always orthogonal to each other. In our next example, we're looking at two-dimensional motion in a gravitational field. We are given the velocity vector and how to get it, and we are also given the position vector and how to get that. I would make a note that seeing as we're going to be using feet in this problem, gravity is going to be equal to 32 feet per second squared, not our traditional 9.8 because that's meters per second. So let's find the position, the velocity between the time it's hit and the time it first hits the ground. So I would like to note that r of t is going to be equal to, now I will note that u naught and v naught are both 80. So u naught is 80 t plus x naught. We're going to say that this is hit at, we're going to say where it's hit is at a position where x is 0 and y is at 3 feet. So this would, my x naught for this would be 0, and then -1/2 g, which is 32 t squared, plus v naught we were given, that is 80 t, plus y naught is 3. So making that look just a little prettier, cleaning it up, that would be 80 t minus 16 t squared plus 80 t plus 3. Now our velocity vector is going to be the derivative of our position vector, so that would be 80 -32t plus 80. So we've got our A part done right here. Okay, and it's going to look somewhat like this if I carry this all the way out. This is going to be the path of the ball. B says show that the trajectory of the ball is a segment of a parabola. So what I'm going to do is note that x equals 80 t for the position and y equals -16 t squared plus 80 t plus 3. Writing this in terms of x, let's note that t equals x over 80. And then I'm going to substitute into y. Quantity squared plus 80 x over 80 plus 3. You can note that this is a quadratic, and because it's a quadratic, it's going to make a parabola. I'll simplify it. There it is, simplified. The C part wants us to figure out how far it travels horizontally, so I need to know when it hits the ground, so I just need to know when x is 0. So I'll use the quadratic formula here, and if you use the quadratic formula, or I'll just use my calculator to calculate that 0, I'll get that for you. So I had my calculator go ahead and get that right hand 0, and my calculator got that t equals 5.04 seconds is when it hits the ground, so that's at 5.04 seconds. Then they want to know how far does it travel horizontally, so that would be x of t equals, and looking up here, that is the 80 times the t, which would be, write that a little prettier. Alright, I get that horizontal distance to be 403 feet. D says what's the maximum height of the ball, so I'm going to be looking at y of t, and y of t is, let's see, negative 16t squared plus 80t plus 3. I just need to know that critical point to get the maximum. Y prime of t is negative 32t plus 80, and I need to see where that equals 0, and that t value would then be at 2.5 seconds. They don't want to know when, they want to know what it is, so I need to do y of 2.5 and crunch those numbers. Times 2.5. So I got 103 feet for that height. E says that does the ball clear 20-foot fence? That's 380 feet. Alright, so what time is that at x of t when x is 380 and that x function was 80t? So that means when t equals, and that would be 4.75 seconds, and I need to know how high it is, so just y of 4.75. I'll get that. Alright, I got 22 feet when I plugged that in, so yes, it would clear that fence. Alright, yes, right there. Alright, on to the next one. Let's read through the problem and pick out our pieces here. Initial speed, so that would be the magnitude, our velocity vector there, and that would be equal to 55. We're in meters per second, so gravity is going to be 9.8. Our angle alpha is going to be 25 degrees. Ooh. Okay. How far does the ball travel horizontally, and when does it land? Horizontally would be range, and I'm just going to plop in those numbers. Right, get 236 meters. When does it land? That would be time of flight. I'll plop in those numbers. Right, I get 4.7 seconds. The B part asks what's the maximum height of the ball. I'll use the maximum height formula given. I get that max height is 27.6 meters. The C question says at what angle should the ball be hit to reach 300 meters from the tee. So I guess we have a new angle now, and our range is now 300, and I'll use the range formula and plop that in. Alright, and using inverse sine and solving for alpha, you'll get about 51.8 degrees. Okay, last one is up next. We have a projectile that's been fired, and what we've been given is we've been given an acceleration vector, and that acceleration vector is in the x direction. There is 0, and of course this is only being acted on by gravity, so except for, and that is in that z direction, except for the fact that we have a crosswind that's blowing us north, and that's in the y direction, so that would be 0.36 here. And then we have the gravity acceleration. We know that velocity is the integral of acceleration. So we could say that this is here, and then we know that we would have 0.36 t plus some constant 1, and then negative 9.8 t plus some constant 2. Oh, and I could have a constant here, so we'll call, I probably should do that 1, we'll call this 2, and we'll call this 3 to make it a little better. And then I'll fix my writing. So let's try to figure out what V naught, V at times 0. in that x direction, that's going to be your cosine. So that's 300 times the cosine of 30 degrees. And north and south, we don't have any effect as of yet. And then in this z direction, this vertical direction, it's going to be 300 sine of 30 degrees. What I get for this is then 150 square root 3, a 0, and a 150. I can now plug these into my velocity vector, because at time 0 they will just then be those constants. So it'd be 150 square root 3. I'm going to write that down. So I found my velocity vector. Next up is to find my position vector. And that will once again have some constants. So 150 square root of 3t plus c1, and I'm going to write all the rest of them down. Alright, almost didn't have enough room for that, but then I did. Okay, at time 0, my position vector is going to be at our origin. This means that each of these constants is 0. Okay, I finally got to there. The question was, where does the projectile land? It lands when this quantity right here, this z direction, is equal to 0. So I will solve that thing, and I will then get, hold on. Okay, so I finally got the time that it lands. Now I need to get where it lands, and to get where it lands I will need to plug that into both the x and the y, and I'll get an x coordinate and then I'll get a y coordinate. Okay, after plugging that in, I find that the projectile lands 7,953 meters away and 169 meters north of where it was fired. Alright, let's read this next part. Oh, first let's address this two-dimensional motion here. Why is it that two-dimensional motion couldn't be used with this projectile motion? That is due to the fact that we had a crosswind, and instead of making this two-dimensional motion, it was then made three-dimensional motion due to this crosswind. This makes it so that this cannot be used. For this last part, we're going to be looking at the x and y components, because the z component isn't really affected. We just want it to land on the x-axis and not due north, so we want that y of t component to be equal to 0. So if I look at x of t, so that means our time is still going to be the same. If I look at that x of t, he's going to break down into cosine of whatever theta that we're wanting, and then y of t is going to be equal to the same thing with a but with sine of t wherever it is that I have that t listed. So let me get that written down. With our t still equal to that 30.6 seconds, we want y of t to be 0, and 30.6 seconds, and we'll plop that in. We're going to solve for theta. So when we crunch those numbers, we find that theta is negative 1.21 degrees, so we note that it must be fired so that it is 1.21 degrees south of your east. And that concludes that one. 12.7.